to the cloud. And I'm going to share my screen. All right. We are live for lecture 5, an introduction to digital communication. And this will, broadly speaking, be our thing for the entirety of winter quarter, really, where the most of our lectures will be talking about the other side of our system, the digital communication. Um, and a few announcements really quick. Design reviews are in progress. We've had 2 design reviews so far, really good work by both the teams that we've been able to talk to. It'll obviously be an iterative process, and we hope you keep working with us. It's been awesome to see the stuff you guys have put together so far. A rough timeline for winter then, in terms of the different things that you'll be juggling in your teams. We'll have these lectures and assignments that come with them, obviously. In terms of the design reviews, those will continue happening in parallel. Ideally, we want to have you guys in a position where we can submit parts orders in week 9 of winter. What that means is having PCB laid out boards for both your transmitter and receiver, along with a bill of materials by the end of week 9 of winter, so that we can submit the parts order then, giving week 10, finals week, and spring break as time for the parts to come in. What that means in terms of real deadlines you should probably set for yourself. Realistically, you want to finish the schematic reviews by week 4, week 5, so that you have enough time for 2 iterations of the PCB layout. And you also probably want to start working on a bill of materials relatively soon, so that you don't have to do it all in one go towards the end. To help with the process of the bill of materials, Tyler will be sharing our bill of materials from our prototype. And you can use that as a starting point, see some of the values we found, and use that as a starting point to get started. Yes, a starting point to get started. Jesus Christ. But yeah, those just so you know, any parts on there are also parts that will most likely be available to you, because we built a stock of those parts by ordering enough to build multiple versions of our boards. So those are stock parts that will also be available to you if you want to use them. Finally, before we get started to this lecture, I want to clear expectations about what you can expect from this lecture and this set of lectures in general. Let's be clear about the fact that we'll probably have 3, 4 lectures in this quarter maybe, and you have 2 a week in ECE 113A and ECE 132A, basically covering the material we'll be doing in a cumulative 4, 5, 6 hours. This will not be as in depth. There will be a lot of math that we will be hand waving over and looking at the final results. There will be a lot of things that, for the purposes of the lecture, we will ask you to accept as given fact. I really recommend taking 132A if any of these lectures are interesting to you, because it's a really interesting class that goes over a lot of this material in much more detail, so that you can be more satisfied in proving it to yourself. Similar to the first quarter, if there's any part of it that's interesting to you, come talk to either of us and we can point you to other reading resources, other YouTube videos that go into it in much more depth, and a whole bunch of stuff you can do to learn more about it if it catches your fancy. And with that, let's get started. Here's what we'll be talking about today. We'll be doing some introductory work as to what our overall digital communication system looks like, similar to what we did for the analog system at the start of last quarter. We'll be doing some groundwork and basic math that we'll need to develop a notation system. That's quadrature modulation, demodulation, and the complex baseband. And once we have that notation, we'll be using that notation to discuss our system. We'll be using a kind of symbol mapping called binary phase shift keying, BPSK. And we'll be talking about InterSymbol interference and pulse shaping and what all of those things mean and why they're important.
All right, with that, let's get started. So before we get into all the math and everything, let's go example and premise. Let's say on microcontroller A of data 01000101, whatever, and we want to communicate that to microcontroller B. So we're trying to think of how we might do that. Maybe we can look to a real life example of wireless communication for some inspiration. So if you and your friend were standing far apart, could see each other, but were too far to hear each other, but you had flashlights so you could communicate by turning them on and off. One way you might decide on to communicate with one another is to use Morse code by pulsing the lights on for short and long pulses. You can communicate English letters to one another. So in this example, we have 26 letters and they're mapped to distinct sequences of short and long pulses. And in RAP, defining some terms, so those sequences that we're mapping information to are going to be called symbols. So going back to the electronics context, symbols are unique waveforms tied to a string of bits. One way you might think of, okay, so if I just connect a wire between two microcontrollers, and then I use 5 volts to represent 1, 0 volts to represent 0, turn on and off over time, and you might not have, that should work fine. The problems come in when you take the wire out and you're trying to communicate wirelessly. We kind of motivated this way back in fall when we said like, hey, if your information is at too low a frequency, you can't really broadcast it over antenna. You need to modulate it up to a higher frequency carrier if you want to have a reasonably sized antenna. And there's some other issues with using this kind of square wave representation that we'll get into later in this lecture. Just a little sneak peek of what we might end up doing. There's a lot of different communication schemes with different symbols out there, but one that we're going to be using in RAP is called BPSK, Binary Phase Shift Keying. It's a fancy name, but all it really boils down to is we're going to represent our bits, our 1s and 0s, as different phases of a sinusoid. So like you can see in the figure in the bottom left, when it's a 1, the phase is 0, and then for a 0, the phase flips. Now it's 180 degrees, it's inverted. You can represent this modulation scheme using what's called constellation diagrams. You can see on the bottom right, but to really understand what these diagrams are showing, we need to dive into something called Quadrature Modulation. And Vaibhav, go ahead and take that away.
All right. So let's start in the most generic terms, right? The one thing that we're not going to get into here is frequency modulation. We're going to assume that our signal is being transmitted at a given frequency, right? So start by considering any arbitrary, does this thing give me a pointer? Yes. All right. Start by considering any phase and amplitude modulated signal. Can you guys see the pointer? God damn it. Can you guys see the pointer?
Yeah, we can.
All right, fantastic. So start by considering some arbitrary phase and amplitude modulated signal. A of t is the amplitude modulation, phi of t is the phase modulation. These are independent of one another, just obvious constraints of 0 to 360 and other such things, but they can be pretty much any time series of whatever data you have. There is a question in the chat. No, yes, well, fuck you, Sahil. All right, so so x of t, this using some pretty straightforward trigonometry can be rewritten as a of t cosine theta t cosine, you can rewrite it as this, fairly straightforward. And here we're going to define two terms, the in phase term, which is a of t cosine theta of t, and the quadrature term, which is a of t sine theta of t. All right. In phase and quadrature, just because sine and cosine are slightly meaningless terms to use in an RF system, just because whether it's a sine or a cosine will often depend on when you start measuring the signal. And because these signals extend infinitely in both directions, whenever you start sampling, or at least for our purposes, infinitely in both directions whenever you start sampling. So it's a bit more useful to define one term as being in the phase of whatever you're measuring, and then one term being, quadrature or 90 degrees with respect to that. So we have in phase and quadrature terms, and we can rewrite our signal as I of t cosine omega naught t plus, or minus some constant here again times sine omega naught of t. The key takeaway from this math and why it's particularly important is because I of t and q of t are now again just time series of amplitude modulation. And so the key takeaway of this is that any arbitrary amplitude and phase modulation can be applied simultaneously simply by summing two amplitude modulated cosine and sine waves. As long as you choose those amplitude modulations for those two in an intelligent manner, you can construct any arbitrary amplitude and phase modulation simply by amplitude modulating. You don't have to find a complicated way to add time delays and phase shifts to your signal. All right. So quadrature demodulation then, which is at the receiver end, right? If we're writing our transmitted signal in terms of this I of t and q of t, and we're saying that all the modulation information is contained in this I and q of t, probably important to be able to figure it out even at the receiver end. And so again, if you take x of t and multiply it by cosine omega naught t, and I'm leaving this here as a reminder so that you can keep referring to it. If you take x of t and multiply it with cosine omega naught of t, where omega naught is whatever carrier frequency or symbol frequency, whatever you have, again, you rewrite it as these terms, use some simple trigonometry. And when you low pass filter this, you get rid of these double frequency terms. So you get rid of the cosine 2 omega naught t, and you get rid of the sine 2 omega naught t term, and you're simply left with 1/2 I of t. You do a similar thing by multiplying it with a negative sine of omega naught t, and you can similarly extract q of t or half of q of t um, by low pass filtering this expression here, because again, you get rid of these double frequency terms. And you are able to generate these two because we're assuming you at the very least know the frequency at which your transmitter is operating, because we're designing the transmitter. You're designing this communication system, you're choosing what frequency it's working at. So omega naught is in fact known to you. Now from I of t and q of t, based on these definitions, you can again find a of t and theta of t. It's pretty simple trigonometry. You square them, sum them, take the square root, you get a of t, or half of a of t in this case. But that's a meaningless difference. You divide them by one another and do the tan inverse, and you have theta of t. And so from these two terms, you can find a of t and theta of t. So again, the key takeaway from this slide and the previous slide combined is one, you represent any arbitrary amplitude and phase modulation just in terms of amplitude modulation. And two, as a function of doing that, you are able to extract the modulation information. That is, you are able to extract the actual signal on top of your carrier wave without really needing to worry about what the carrier frequency is. You can reconstruct the entirety of the information you're transmitting without having to worry about doing these operations with the carrier frequency in mind. Which brings us in part to this pretty powerful idea of complex baseband, right? Which is, if we're saying that all the information we need is in I of t and q of t, let's simplify our notation. Let's get rid of this omega naught t that's kind of floating around. So if everyone's taken 110, you should be familiar with phasor notation. And this is kind of an analog of that, where you're rewriting x of t as the real part of a complex phasor. Guys, I can't keep opening the chat, so if you could ask your questions verbally, that would also. Oh, have not taken 110. Um, that it's more. It's not necessary to understand this slide. If you're familiar with what was it, De Moivre's, De Morgan's, someone's theorem, a complex exponential can be written as the sum of a real cosine and an imaginary sine. If you take a complex exponential and then you extract the real part of it, you're essentially getting cosine omega naught t plus theta t, which is what we defined x of t as. So you can rewrite x of t as the real part of this complex exponential. You can even take a of t out of these brackets because it's purely real, but it doesn't really matter. You can leave it on either side of this. Rearranging terms, I'm sorry, there should be a j there. So this should be e of t j theta t, e of j omega naught t. I will fix that before releasing these slides. You can rewrite this as, and this is just a definition where we're saying x baseband or xbb is a of t e to the j theta t. Again, this is just something we're defining. It's a new variable we're creating. This is called the analytical signal, where xbb is then I of t plus j q of t. And this is, again, notation we're creating. So what this basically lets us do is say, all right, irrespective of what frequency our system is operating at, we can do all our work of taking our bits, converting them to symbols, coming up with a mapping to symbols, and then decoding from symbols back to bits. We can do all of that math at DC. We can do that at baseband, right? Baseband being at zero frequency. And we can abstract away the fact that we're transmitting at this omega naught frequency. We can abstract that away and simply use this notation to talk about all of our symbols. This is actually a really important idea. So if anything up to this point hasn't made sense, please ask now. All right, fantastic.
Can I ask, like, but the previous slide you ended up with like I of t over 2 and q of t over 2. I get how you got up to there, but then how does that translate to the a of t?
Sure. So if you look at here, how we've defined I of t and q of t, right? If you were to square these terms and add them, the cosine theta of t and sine theta of t would add up to 1, and you would simply be left with a square t. So I square t plus q square t is a square t. And so what you do from yi and yq is square them and add them, and then take the square root and then multiply with 2.
Oh, okay, yes, I see where a of t is from now.
Right, and for theta of t, we do something similar where we're simply manipulating our trigonometry. So what we do is we take yq and we divide that by yi, and that gives us tan theta of t, and then we take the tan inverse of that to get theta of t.
I can't do trig in my head, but I'll trust you.
No, we can. All right, yeah, you can write it out, and you'll see that the ratio of q of t and I of t works out to tan of theta of t, and you can simply perform the tan inverse operation on that. All right, so just one last logistical note, and I've noted this here as well. Baseband signals have a complex part. However, it's important to keep in mind that this is a mathematical notation similar to how we developed complex phasors to talk about circuits. At the end of the day, if a current is flowing in a wire, it's purely real. If a voltage is measurable between two nodes, it's purely real. If a signal is flying through the air, it is in fact real. This is notation that helps us deal with these things without having to drag a lot of additional math all over the place, but it's important to visualize in your head, or it can be useful to visualize in your head that you are only transmitting a real signal.
Wait, can you explain again the complex baseband and how you get to the x of t being the real part of that complex number?
Sure. So if we go back a couple slides, we've defined x of t as this, a signal with arbitrary phase and amplitude modulation. And this here is simply the real part of a complex number, a of t cosine omega naught t plus theta of t plus j sine a of t, or j a of t sine omega naught t plus theta of t. right?
Yeah,
So
okay, yeah.
if you take this and you take the same argument and you do plus j a of t sine that same argument, that like cosine x plus j sine x is e to the jx.
Yeah.
Right? So we're simply using that idea where we're saying, all right, the real part of e to the jx is simply cosine x. And so then we say the real part, this is a sum in the exponential. So like I said, there should be a j here, but then x of t is then the real part of a of t multiplied by e to the j theta t plus e to the j omega naught t. And then we
Oh,
are
so because it was
defining,
cosine, okay, so you just simplified the cosine as the real part of a complex.
yes,
Okay,
yes.
okay, that makes sense.
Yeah, and then we're defining x baseband, this capital X baseband, as simply being a of t e to the j theta of t. And then by that definition of, a of t and theta of t, we can then again get that x baseband is a of t cosine theta of t plus j a of t sine theta of t, which is our definitions of I of t and q of t.
Okay.
All right. Are there any other questions? All right, I'm going to move on for now then. And if there are any questions that come up, we can always revisit these slides. These are pretty important to understand for just for being able to work with digital communication. So any questions are welcome. So Tyler earlier mentioned constellation diagrams. You can think of these as a way to visualize systems and to systematically generate symbols, right? So we said, all right, symbols are this idea of assigning a unique waveform to any string of bits. But we also know that if you have a certain number of symbols, that also constrains how many bits you can assign to those symbols. What that means is if you want a higher bit rate, which means if you want more bits per symbol, you need to start coming up with ways of systematically generating those symbols. Because the obvious way of, well, the first symbol is x of t and the next symbol is twice of x of t and then it's 3 times of x of t, then it's 4 times of x of t. Like you start very quickly running into constraints of how much power you have to transmit and things like that. So you need a systematic way to keep track of them, generate them, think of them. And that's where constellation diagrams are helpful, along with letting you compute things like error rates and many other things that 132A covers. So they're a way to visualize systems that have many symbols. Each symbol can be thought of as basically a unique value for X baseband, right? Because each symbol is basically a unique modulation. It's a unique waveform on that carrier wave, and it's a unique modulation. And since we already discussed that all our information of modulation can be captured by that single constant X baseband through those 3 slides of math we just discussed, what we can think of each symbol as is a unique value of X baseband that can be depicted on a real and imaginary axis, or an axis of I and Q. So what that means for BPSK is 2 values, 1 and -1. You also have other more complicated forms of modulation or mapping. This is 4QAM, which is 4 quadrature amplitude modulation, where you have bits mapped to 1 phase shifted by 45, 135, 225, and 315 degrees. Right? Yeah. So at different phase shifts. And then you make that even more complicated with 16 QAM, where you add the ability to phase and amplitude modulate all at the same time. So, you're basically doing a whole bunch of phase amplitude modulation simultaneously, and you're depicting these symbols as unique X baseband values because X baseband contains all of our modulation information. So these are useful. We won't see them too much in this project because our modulation scheme is fairly easy to keep track of. But like I said, if you take 132A, there's actually a lot of useful information you can get from these. One cool thing is that by defining the distance between these 2 points and by defining like the distance between the origin and this point, you can get a mathematical relationship between the power of your signal being transmitted and your error rate, which is useful to know, which is, all right, if I run my system at 10 watts, or, you can convert the 10 watts then down to say 3 volts or whatever, what's my error rate versus what if I run my system at 9 volts and 100 watts, what's my error rate for that, and so on and so forth. And that's a really useful thing to when you're designing a real system. And these make it very easy to find that information.
Just quick, what's the difference between constellation 1 and constellation 2 on the top? Like the one which goes 0, 180, and then 90
Right.
minus 90.
For our purposes, none. It's just that or for practical purposes, none. It's more that if you think of having defined in your mind the in phase and quadrature term as being, cosine or sine, these are at a phase shift from those. So it would be along a different axis. So instead of being, +1 or -1, it would be j and minus j.
Yeah.
Right.
Yeah.
So it's in terms of it kind of just changes how you're creating your modulation signal.
Okay.
But in terms of properties, they're about the same.
Okay, that makes
They're
sense.
just different ideas of forms of
Mhm.
BPSK, you can say. All right. So now that we know that our BPSK values are 1 and -1, so -1 is this seems to be inverted. That is my bad. But we're going to be using -1 to talk about zeros and 1 to talk about ones. Now that we know that, it's like, well, all right, so we have this where we're saying, all right, so let's say we have this amount of time, whatever time it is. So there look to be about, say, 10 or 15 of these in 0.2 seconds. So some transmission rate. There's some number of symbols per second, and we know that those symbols can be represented as values of x baseband. So if we think of x baseband as these delta functions in time at intervals constant t, where constant t is our transmission rate, then all right, for BPSK we're transmitting 1, 1, -1, 1, -1, minus so on, depending on whatever our binary string is. Similarly, if you had 4-clamp, for example, you might transmit 1 with a phase shift of 45, 1 with a phase shift of 135, and 1 with whatever phase shift is necessary, and you might represent it with these delta functions then as a time series of delta functions. And so this is where we're at so far, where we have, all right, this is the information I want to send. I have mapped the information I want to send to these symbols, and I know that I want to send these symbols at these intervals of time depending on what my desired transmission rate is. And now I am going to say that I'm going to basically convolve those symbols with these delta functions, and they're not two delta functions, they're called I forget the name, some type of delta function, but basically they're capped at 1 and -1 instead of going to infinity. But for that's the only difference. So now we're saying that, all right, we have this time series of delta functions, or a delta train, that captures all my modulation information by using this x baseband notation. From here on out, what we're going to discuss is, all right, now that I have this delta train, how do I transmit it?
Okay, so kind of what I was getting at earlier. Okay, do we just send a square wave where each of these deltas, either 1 or -1, is like a rectangular signal, and then do we just multiply that by our carrier wave and then send that out? That sounds like it might makes sense. And that's kind of what the figure way back was showing, where the phase of the carrier was instantly flipping. But in practice, that we run into some issues with that, and that's because real physical channels are band limited. So if you remember from perhaps 102, a square wave with infinitely fast transitions has essentially infinite bandwidth, and a band limited channel might not necessarily have a linear frequency response for all frequencies. Maybe higher frequencies start getting treated differently than others. So what does that mean? It means if I try to send a square pulse along something, then we'll get smeared out a bit. And if there's multiple, like let's say I have a sequence 101, and they start smearing into each other, then maybe where that 0 was might not look like a 0 so much. And then it becomes hard, then on the receiver end, it might become hard to distinguish between what's one symbol versus what's another symbol. Okay, so we need to come up with a different window choice for our system, and we can't just pick any random window to convolve with our delta train. The window we choose must meet a criteria called the Nyquist InterSymbol Interference Criterion. So what the heck does that mean? Basically, that's saying that the impulse response of this whatever window we choose should be 1 at a index 0 and 0 elsewhere. So one example of that might be a sinc function. If you if you want a laser pointer at n equals 0, it has a magnitude of 1, but then at each interval, sampling interval thereafter, it's going to have a magnitude of 0. Now, sinc function has some issues because it has an infinitely long impulse response, which we can't really realize in a digital system. Just a quick note, I was talking to Vaibhav earlier. Technically, I believe the rectangle function does satisfy this criterion, where it is 1, the impulse response is 1 at 1 and 0 elsewhere. But since it has infinitely fast transitions, the whole band limited channel problem makes that not possible. Yeah. So so instead of a sinc, instead of a rectangle function, we have something else to show you guys. So go ahead, Vaibhav.
Yeah. So what we're going to be using is something called a raised cosine filter. Mathematically, it's this. It's a thing. It's a useful thing to know, and you will use it when you start coding this function onto your microcontrollers. I think for the first part of our discussion, when we're going to be simulating on MATLAB, I think MATLAB just has a raised cosine function filter, but you can look that up. I'm sure it exists. It's called the raised cosine because it rises with a cosine term and then it flattens for its central bandwidth, and then it falls like a cosine term again. Beta is a factor that controls the roll-off basically being the cosine part that's decaying away and rising up to our central flat portion of the frequency response. Its impulse response is, again, crucially, it's 0 at all other integer multiples of whatever sampling point we choose, depending on how we define this filter. So that's our raised cosine filter, and this is what we're going to be using. Now, I promised you guys we would have some hand waving and some pointing to please take 132A. This is, I think, the first big place where we're going to do it. Suffice to say that we get the best performance of our channel from a signal to noise ratio perspective when we have a filter that is matched, that is our filter, if it is identical at our receiver and our transmitter, that is when our channel as a whole performs the best. Our system as a whole gives us the best signal to noise ratio when we have a matched filter. And that's what it's called. It's called a matched filter. So, well, if we want our overall system to have a raised cosine, it seems, well, why not stick half the raised cosine at the transmission and the other half of the raised cosine at the receiving filter? And that's what we do. And that's what gives rise to the root raised cosine. And again, you take all that fancy math here, stick it under a square root symbol, and there's your root raised cosine. And the root raised cosine is what you use as your pulse shape at the transmitter, and it's what you use to window your input at the receiving filter as well, when you then start reading for ones and zeros. So in practice then, or well, in simulation at least, this is something like what that would look like. Here you have your delta train. You then have your root raised cosine, and this orange signal here is what would get modulated onto your 1 megahertz output from the microcontroller, or rather this would be at 1 megahertz. This would get modulated onto your 4, so give you 5, then you go up to 27, you transmit it, you down convert, at 1 megahertz, you feed it back in. So this is what goes into your boards that you have been and will continue designing. And then when you take the matched filter and again convolve it with this same filter, you get the raised cosine. And this is really nifty because you can see that at all our sampling points, it intersects exactly the value we want. And so this is basically why we've chosen this pretty powerful window. People far cleverer than us have done the math, and a lot of that math is again discussed in 132 as to how all of it works. But suffice to say, what using the root raised cosine and using it as a matched filter pair gives us is something that performs really well in terms of being able to transmit our delta train of symbols, and does so in a way that doesn't run afoul of the InterSymbol Interference criterion. Does all of that make sense?
In the graph, what are you convolving with what again? The 1 megahertz signal is convolved with the deltas to get the tall signal that you see there. Is that correct?
No, so you have deltas, and that delta train is well
Vaibhav, I can
typically
take this.
okay.
Yeah, so the delta train, which is our sequence of deltas, they're either have magnitude 1 or amplitude 1 or angle 1, right?
Mhm.
You convolve that with the impulse response of the root raised cosine. Okay.
Okay.
And then Vaibhav, go to the next slide. Yeah, so that gives you that orange signal there. What you do next,
Wait,
it's
can you
not shown
point to
here.
the orange signal? Just which one is it?
Yeah, that lower end. So
Okay, so
yeah.
convolving the delta
Or-
with the impulse
yes.
response gives you that.
Yes.
Okay.
Am I reading this right? Yes. No. The raise cosine. Yeah. Okay. What you do next is it's not shown here. Then you modulate onto your carrier frequency. So you have that orange signal there. You
Mhm.
just times a sinusoid, a complex exponential of 1 megahertz. That will, when you generate your samples from that, you output that from your digital to analog converter into your board. That goes through, gets sent over the air, received, and then on the receiver end, hopefully you have something like this, but it's been put onto 1 megahertz. and then you demodulate, then you put it through the digital filter, you put it through another root raised cosine filter, then you'll have something that looks like the yellow signal, hopefully. And then you do the quadrature demodulation to get your symbols back, and then from there you figure out what your bits were.
Oh, okay, that makes
is-
sense. So the taller yellow signal that I see there, that one's what you would get at the receiver end when you.
Yeah, after you go through first both root raised cosine filters, so they're both a square root. The frequency domain, they get multiplied. You get your just the regular raised cosine filter.
Yeah.
Okay. Okay. I hopefully that answers your question.
No, I think that makes sense now. Yeah, thanks.
Mhm. Okay. The next slide kind of basically just spells out what we just went through. So it's just a step-by-step instructions what to do, and we'll have this much more concrete in the form of a MATLAB assignment coming up in not too long. Yeah, okay. Bye, Bob.
Yeah. Some of you may have noticed that Tyler for a second there brushed over one thing he said, which is assuming you can reconstruct the signal as is, and that's something we'll talk about as well, which is, well, we've talked about attenuation in the physical design, but that's obviously not the only non-ideality you get from your channel. There's going to be other things as well, so we're going to be talking about that in future lectures, about other noise and other imperfections that the channel can add and how to fix those and mitigate their impact on our digital scheme. For now, though, we will have a simpler assignment that kind of models an ideal channel in MATLAB and basically walks you through the steps of generating this very plot. That's the bare bones of of the code that you would eventually put on your microcontroller as well. And while there's some extra steps on the receiving end and maybe a few on the transmitting end as well, give or take, this is almost the bulk of the code you would at least be putting on your transmitting microcontroller, for example, only in eventually C instead of MATLAB. So yeah, that's all we have for you guys today. We wanted to just introduce the basics of the digital communication scheme we're going to be using, some notation that will keep coming up, why we're able to use that notation, some of the math to justify what it means and to help guide your intuition for what that notation represents. A reminder that we have a couple more design reviews with some of you tomorrow, and we'll likely keep meeting with you over the next few weeks, like we discussed in that initial discussion of the winter timeline. Given that we're only going to be finishing the first round of design reviews tomorrow, we're also going to be releasing assignment 5, either late tomorrow night or potentially early Saturday morning. But that's when assignment 5 will go live. Similar timelines of you'll have 2 weeks between each assignment and between each lecture, potentially more depending on how lectures line up exactly with the goals we have for you guys for the physical design. So it'll be flexible. We'll keep in contact with you guys, and we would appreciate any feedback if you ever think the project is becoming too much, / if you have enough time to maybe for us to fit extra stuff in. All of that feedback is always welcome. So yeah, that's all for today. We'll see you guys next time.
Alrighty.